Once a part of the planetary family of our solar system, Pluto is a far-off and enigmatic dwarf planet. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku of MIT, however, have recently made astonishing claims that have thrust Pluto back into the public eye. They imply that the ice world is headed for a collision with Neptune. However, how might this occur, and what would happen if such a significant event occurred? Is there more to this looming cosmic collision, or are we just seeing a unique astronomical phenomenon? Come investigate the potential impact between Pluto and Neptune. The astronomical world is still fascinated by and interested in Pluto, a former planet that was downgraded to a dwarf planet in part because of its unusual orbit. Leading scientists have recently predicted that Pluto's course is perilously close to that of Neptune. Michio Kaku and Neil deGrasse Tyson are both warning of a potentially dangerous collision between these two planets that might endanger Earth greatly. How might such a thing possibly occur? Unlike any other planet in our solar system, Pluto takes an incredible 248 years to complete one circle around the Sun, meaning that since its discovery in 1930, it hasn't even completed one complete round. However, the mystery doesn't end there. Pluto's trajectory is distinguished by its extremely elliptical form, which departs greatly from the larger planet's nearly circular orbits. The inclination of Pluto's orbit, which is 17 degrees from the ecliptic plane, adds to its oddity. Pluto's orbital pattern is made more complex by the fact that it follows a far steeper course than the other planets. The point where Pluto's orbit intersects Neptune's is among its most fascinating features. Contrary to what one might anticipate given their places in the solar system, Pluto actually approaches the Sun more often than Neptune for roughly 20 years in each orbit. The obvious question that follows is why Pluto and Neptune haven't collided. The gravitational pull of other planets holds the solution. Soon after Pluto was discovered, astronomers started studying its orbit. At first, they had trouble comprehending its peculiar path. Pluto's journey stood out due to its steep inclination and elliptical form, in contrast to the other planets whose orbits are generally close to the ecliptic plane. The discovery that Pluto's orbit truly crosses Neptune's added to the puzzle. The complexity of space mechanics is demonstrated by the stability of Pluto's orbit in the face of these complications. The goal of the three-body problem in space is to determine how three celestial bodies, such as the Sun, Neptune, and Pluto, move and interact with one another through gravity. It's similar to attempting to forecast their future direction based on their starting points and mutual pull. This problem illustrates the intricate relationship between Pluto's route, Neptune's path, and the gravity of the Sun. This problem includes the phrases alpha libration and latitude libration, as well as the VZK oscillation. Astrophysicists believe that a phenomenon known as alpha libration is responsible for all planets remaining in their orbits. When referring to Pluto and Neptune, this phrase indicates that Pluto is at least 90 degrees away from Neptune whenever it crosses its orbit. In order to keep their courses from meeting, this space separation is essential. Conversely, the vertical movement of a celestial body within its orbit is referred to as latitude libration. This gives Pluto an extra layer of safety from possible collisions because it is located far above the orbital plane of Neptune or any other massive planet when it approaches them. The VZK oscillation, which bears the names of three scientists who investigated object motion in space, Bond, Zippel, Leo, and Kai, is another essential element in this equation. It concerns the gravitational force of three celestial bodies, the Sun, Neptune, and Pluto, on one another. They move differently as a result of this pulling. The VZK oscillation in Pluto's case explains why its orbit around the Sun is so peculiar. This oscillation keeps Pluto traveling smoothly over extended periods of time, despite the fact that its route appears chaotic. The VZK oscillation demonstrates that despite the appearance of chaos and randomness in space, certain patterns and laws maintain order. These elements all work together to keep Pluto in its orbit and prevent it from colliding with Neptune or veering off course. Understanding how these courses alter as a result of other objects' gravitational pull in space is made easier by this three-body dilemma. Despite these steady characteristics, Pluto's orbit is technically chaotic, with little variations in beginning conditions producing notable variations over millions of years, according to numerical models conducted in the late 1980s. Nevertheless, it has been shown that these special characteristics of Pluto's orbit preserve stability over extraordinarily long timescales, thereby containing the chaos. We now have a better understanding of how large planets like Jupiter, Saturn, and Neptune impact Pluto's orbit around the Sun thanks to recent computer tests. Because of their unique relationship, Neptune completes 3 orbits around the Sun for every 2 that Pluto completes. In addition to Neptune, Jupiter's gravity also plays a significant role in sustaining Pluto's orbit, with Saturn also making a minor contribution. This relationship helps keep Pluto's route constant. These experiments demonstrate that Pluto will remain on a stable course for many years, possibly billions of years, thanks to Jupiter's powerful gravity alone. It appears as though Neptune, Jupiter, and Saturn are cooperating to keep Pluto traveling through space securely and trouble-free. The order and predictability of the motions of space bodies depend on these occurrences. The solar system as we know it would be far more chaotic and unpredictable without these systems. Pluto and other bodies may clash with one another or be ejected from their stable courses, which might have a cascading effect on other celestial bodies. Understanding Pluto's orbit is crucial, particularly in light of discussions about it potentially colliding with Neptune in the future. This helps us better understand how dynamic the solar system is. Pluto serves as an example of how the intricate interaction of orbital mechanics and gravity can bring even the most seemingly unstable orbits into balance. It also demonstrates how crucial it is to keep an eye on and research these events in order to better understand our place in the cosmos. Pluto's orbit is a perfect illustration of the unpredictability of celestial entities, which is something we frequently encounter while venturing into the depths of space. Pluto provides a striking example of the idea of orbital chaos, which describes the delicate reliance of a celestial body's trajectory on its beginning conditions. This implies that the long-term course of the dwarf planet across the enormous expanse of our solar system can be drastically altered by even little changes in its position or velocity. Pluto holds a special place that tests our knowledge of planetary dynamics and classification. Pluto has been the subject of much research since its discovery in 1930, which has produced important insights into its makeup and behavior. Pluto's surface, a complicated tapestry of ice, rock, and other substances, is one of its most intriguing aspects. When the New Horizons mission passed Pluto in July 2015, it yielded previously unheard-of information on this far-off planet. Deep valleys, tall mountains, and expansive plains define Pluto's landscape. The Sputnik Planum, a huge heart-shaped plain made mostly of nitrogen ice, is one of its most distinctive features. Large icebergs and what appear to be moving glaciers are among the many geological phenomena that may be seen in this area. Even though Pluto is far from the Sun and has low temperatures, the existence of these features suggests that it may still be geologically active. Pluto's atmosphere, which is mostly nitrogen with traces of carbon monoxide and methane, is another fascinating feature of the planet. Despite having a scant atmosphere, Pluto has intriguing seasonal patterns. Pluto's atmosphere can expand and compress as it moves closer to the Sun in its extended orbit. Pluto and its surroundings have a complex interaction, which is reflected in its dynamic behavior. Some of the atmospheric gases may sublimate back into the atmosphere as it gets farther away from the Sun, while others may freeze out onto the surface during its closest approach. The system is further complicated by the interaction between Pluto and Charon, its largest moon. With a diameter that is almost half that of Pluto, Charon is rather huge. Instead of Pluto merely orbiting Charon, this size ratio indicates that both entities are in a mutual orbit around a point in space that sits between them. This special connection affects the orbits of other objects in the Kuiper belt and adds to the complex gravitational dynamics in the area. Numerous other dwarf planets and possible impactors can be found in the Kuiper belt, an area outside of Neptune that is home to small icy worlds. Scientists can learn more about the development of this belt since it contains remnants of the early solar system. Pluto's orbital features may provide information about the migratory patterns of these far-off objects, indicating that their current orbits may have been significantly shaped by interactions with larger planets. The possible influence on our understanding of the evolution of the solar system is one of the main ramifications of comprehending Pluto's orbital mechanics. Smaller things, especially those in the Kuiper belt, can have their trajectories changed by the gravitational pull of adjacent big planets like Jupiter and Neptune. These encounters may cause orbital changes, which may result in solar system collisions or ejections. Researchers may find more general patterns governing the behavior of celestial bodies throughout the galaxy as they continue to examine the subtleties of these interactions. Philosophical concerns regarding astronomical taxonomy are also brought up by the study of Pluto. The contentious 2006 decision to reclassify Pluto as a dwarf planet sparked discussions regarding the definition of a planet. Many people question the ramifications of such classifications because the International Astronomical Union's definition concentrated on factors like size and orbital dominance. This continuous discussion underscores the necessity for a flexible approach to classifying celestial bodies and reflects our growing understanding of the cosmos. Furthermore, Pluto and the Kuiper Belt still present an intriguing frontier for future investigation. Scientists want to deploy more spacecraft to examine not only Pluto but also other far-off objects that have similar orbital properties, thanks to technological advancements and mission planning. These kinds of missions might yield important information about the primordial substances that formed our solar system, which might provide hints as to the beginnings of life on Earth. Another intriguing field of research that relates to our comprehension of Pluto is the function of exoplanets, or planets outside of our solar system. The knowledge gained from researching our own solar system can help astronomers develop hypotheses about planetary formation and habitability when they find more and more exoplanets, especially in the habitable zones of their stars. The circumstances that permit stable orbits, atmosphere retention, and geological activity may reveal information about the possibility of extraterrestrial life. Last but not least, Pluto has continued to pique public curiosity due to its mysterious nature and the breathtaking pictures returned by the New Horizons spacecraft. People all throughout the world have been captivated by the dwarf planet, which has rekindled their admiration for the expanse of space and our place in it. We are reminded of the limitless possibilities the cosmos has to offer as we continue to solve the riddles surrounding Pluto and the other celestial entities that share its region of space. Do Pluto's special qualities go beyond its orbit and physical attributes? It also provides a crucial case study for comprehending the dynamics of celestial bodies and planetary formation. Pluto and other Kuiper Belt objects are thought to have formed together in the early solar system. Analyzing its makeup can help us understand the conditions that prevailed throughout the early stages of the solar system, which may help us develop theories regarding how terrestrial planets like Earth formed. Pluto may contain a subterranean ocean, according to recent research. This discovery could change our knowledge of Pluto's geology and its capacity to support life. The frozen mountains and other parts of Pluto's surface might be made of water ice, which behaves differently than ordinary rock at low temperatures, according to data from the New Horizons probe. This finding raises fascinating concerns regarding the feasibility of life even in such harsh circumstances and encourages more research into the possibility that liquid water exists beneath its icy surface. Furthermore, atmospheric science can learn from Pluto's interactions with its surroundings. Its thin atmosphere's seasonal variations provide a perfect laboratory for researching planetary atmospheric dynamics. How the interaction of solar radiation and the surface can result in intricate weather patterns similar to those seen on larger planets is of special interest to scientists. It is impossible to overestimate how crucial it is to continue monitoring Pluto and other comparable cosmic bodies. We may anticipate a plethora of new data that tests pre-existing theories and broadens our knowledge of planetary science as further missions are planned, such as those aimed at the Kuiper Belt's outer regions. Every new finding completes the picture of the history of our solar system and the mechanisms guiding its development. Pluto continues to be a symbol of the ongoing search for knowledge about our universe as a result of these studies, encouraging both scientists and amateurs to consider the mysteries that exist outside of our terrestrial domain.